The next speaker is Josh Morjan, Executive Director of Engineering and Utilities at UC Davis and a former colleague of mine. Josh is going to present an initiative that is going on at UC Davis and their campus on electrification and decarbonization. Josh, take it away.
All right, great. Thanks, Marco. Yeah, if you were on the last session, this one's going to be a little different. This is kind of taking a big look at district energy. So I'm going to jump right into this, and should be plenty of time for questions at the end as well. If you don't know UC Davis, this is a shot of our core campus here in Davis, California, and we have 5,000 acres, but I'm going to be focusing on the main campus here, which is just part of that. The 1,200 buildings on campus, but I would say about 8 million square feet of the 12 million total square feet is connected to our district energy. That's about 120 buildings. And the total annual utility bill this last year was about $50 million, and about 50,000 people on campus daily. So just to give you a sense of the scale, my name is Josh Morjan. As he said, I'm been here for over 15 years, and one of the projects that's kind of near and dear to my heart has been the conversion of our heating system from steam to hot water. So that's what this is going to be focusing on. When people talk about renewable energy and decarbonization, a lot of the conversation goes kind of immediately to solar energy, and we do have solar. That's a big part of what we're doing. And so I'll briefly touch on that. And this shows a aerial view of our 60-acre solar farm on the south part of the campus. There above the freeway, you can see UC Davis, kind of nestled in next to the city of Davis. And this is a single-axis tracking solar farm down on the south corner of campus. The purpose of this really is it's behind the grid and on the campus. And so what it looks like, this is up close, what it looks like in terms of the summer production compared to our campus demand and electricity. This is from our dashboard, our campus energy education dashboard. You can see the link there if you want to check it out yourself. But this is showing during the summer our electricity demand in the dark green, and then in the yellow, you can see the production from the solar. And it ends up being about 1/2 to 1/3 of our campus demand is what it's meeting, because it's behind the grid there and reducing what we're taking off the grid. But overall, in the course of a year, it's about 15% of our annual electricity load in kWh. So we also have an off-campus solar farm that we get the renewable energy credits for as well. That's about 30 megawatts. And so working with UC Office of the President, I would say decarbonizing our electricity has not been the biggest challenge. I think the much bigger challenge for us and for most campuses has to do with the heating systems. And so I want to talk about that. That's a big part of our decarbonization plan, and it ties into district energy. We actually have 2 district energy systems on the campus. One is out to the west, our National Primate Research Center, which just got a completely new district energy plant. But for today's talk, I'm not going to get into that one. That one is actually pretty interesting and would be a whole nother presentation. We have some low temperature solar thermal tied into heat pumps out there. But on the main campus here, which is the larger red square on the right, that's the core campus with the district energy for heating and cooling. We have just finished the completion of the first phase of a district heating conversion project. And so that's what I'm going to be talking about today is really what have we learned from that, kind of what the process was to get there, how we pitched it to the campus. A lot of campuses want to go this route and have trouble getting funding. We're in the same boat, but we're working through that process. And so I'm going to kind of describe where we're at and where we're going. Just to give you guys a background on the overall district energy systems, we have cooling and heating. And this is shown before any of the conversion of the heating system. But this is our cooling on the left is the chilled water system. They're both about 27 miles of pipe underground. Chilled water has 2 cooling plants tied into it, with 8 chillers and a 5 million gallon thermal energy storage tank there shown in the middle. The heating system is steam, and we have 4 boilers that are tied into that system. We've just finished, as I said, the first phase to convert it to hot water, but we're still making that hot water initially with steam through a heat exchanger until we have a heat recovery chiller plant in, which is in the next phase that we're in design for right now. So just to give you a sense of the scale of these systems, and then the real opportunity when you have 2 district energy systems like this is to try to tie them together, and you can't do that with steam. But you can do that with hot water. And so that's really the opportunity that we're going after. This just shows some of that opportunity in terms of heat recovery. And the blue on the top of the chart is the campus cooling demand over the course of a year, 8760 hours. And the light blue is the cooling that can actually be used for heat recovery. And one of the kind of mind shifts you have to make is that the cooling system is actually a heat collection system. You're collecting heat from all your campus buildings. Unfortunately, without having heat recovery chillers, you're just throwing that heat away through the cooling towers. It's a low grade heat, so it's not very useful unless you can do something with a heat recovery chiller or a heat pump and step it up to a more useful temperature. And so if you can do that, then suddenly your heating load, shown in the red here on the bottom, over the course of a calendar year, you can see the heating of course higher on the negative y-axis in the winter months, but a majority of that heating load, shown in orange here, is what can be met from the heat recovered from the cooling load. So if you have heat recovery chillers, that light blue on the top of the y-axis, that cooling can be captured and provide the heating load that's on the orange on the bottom side of the axis. So we're able to do about 50 to 60% of our heating load just with heat recovered from our cooling system, meaning that's the reduction in our gas demand with this heat recovery chiller plant and hot water instead of steam. So that's the goal. The additional benefit is that with a hot water system, you can do things to meet that additional heating load where you can't recover the cooling. There's not enough cooling going on in the buildings in the winter to meet your full heating demand. That's where the red is shown. That heating load could still be met with the heat recovery chillers if we can find another low temperature source for our chilled water to get it up to 60 degrees. So what we're planning right now is a geo-exchange system where we would pump the water down into the ground into closed loop geo-exchange just to get the chilled water back up to 60 degrees and be able to run our heat recovery chillers in the winter to meet our winter load as well. One important thing is this is also including a hot water thermal energy storage tank, so we can do daily storage, essentially collecting heat through the day when we're cooling, and then providing the heat to the campus in the night and the morning when we're heating, which we do due to our climate. We're doing that throughout the year, have some heating and cooling load because of our diurnal swing in temperatures. So that's really what we're going after with this district energy conversion, and the big opportunity for us is to leverage heat recovery and also provide a pathway to full electrification. This is our consultant put this together just as a kind of an illustration of all the opportunities. You know, when we talk to people about converting from steam to hot water, a lot of people think it's not that much different. You know, what's the difference? Steam and hot water, it's a different temperature, but that temperature is important. And at the lower temperature, our hot water design temperature right now is 160 degrees Fahrenheit. And there's a lot you can do to both make hot water from different sources, and also, like I said, even raise your chill water temperature, capture low grade heat sources with your chilled water, where then you're able to run it through a water to water heat pump and produce hot water from that low grade heat source, like our chilled water. So this just shows there's a lot of potential, and you really can open the door to tapping into some of that when you have district energy, thermal energy storage, and low temperature hot water instead of steam. So that's the point there. So kind of summarizing where we're at right now is the campus has seen, as far as decarbonization and our fossil fuel free planning, the pathway to go that direction is really through this hot water project. It's the biggest step we can take with the majority of our buildings on district heating. And this shows what we've been doing as a campus is we have a whole campaign and program that's called the Big Shift. Because it is pretty invasive to the campus, we're having to put new pipe in the ground and dig up a lot of the campus. And so we've made it really turned it into a positive and where we can explain, what we're doing with this project. We're not only renewing our heating systems, but we're actually on a pathway to carbon neutrality and decarbonization. So this shows also on the bottom the pipelines we're putting in. They're a high temperature HDPE pipe, which is called PERT pipe, which we landed on after looking pretty closely at the other alternatives, which some of the other campuses have done, which is the European standard thin wall steel pipe, pre-insulated. This one had some advantages. One, just being corrosion resistance, obviously, and water chemistry, not having to be as much of an issue as with the thin wall steel pipe. Cost of installation and the speed of installation going in a lot faster with this compared to the welding of the thin wall steel, which requires some specialized labor as well. So I think there's a lot of different ways to do it. And I think there'll be more and more as we go forward. In our smaller primate center district energy system, we were able to put in PEX pipe, and you can do that pre-insulated or insulated after the fact as well. So some options there on the actual piping. But the process we went through in doing this, just to summarize, was looking at really the lowest life cycle cost for our heating system. And it became very clear as we did that in the master planning stages that hot water with a centralized heat recovery was by far for us the lowest life cycle cost. And there's a lot of ways you can tap into these low temperature heat sources then with that type of system, including your cooling system. Overall system efficiency goes through the roof, and it does provide that pathway to full electrification. So for others that are looking at doing this, I definitely recommend starting with the master plan, but then going to accomplish it. In our case, in a sort of district by district, we broke it into phases that we could work through in I would say bite-sized pieces, because we don't have $500 million to do the whole thing at once. So let me talk a little bit about that. This is our core campus here with the buildings that are connected to district energy shown in color, and the heating system. And this is how we broke it up in terms of phases to make it something that we could actually fund and move forward with, rather than waiting for the funding for the whole project. And so I think that's a really important approach is that we got this first phase done, which is the quad district in red here. One of the reasons we wanted to move that forward is we thought we could learn a lot from the process, both in terms of contractors, implementation, building conversions, getting pipe in the ground, how hard is it actually going to be, get the costs dialed in, and all of that is really helping us to build out the rest of the project in terms of costs and timeline and impact and savings as well. So that one is done, and we're in design for phase 2, which is the yellow, which is going to bid out early this year, starting implementation hopefully in the middle of the year in terms of construction. And then we'll be done with essentially the north half of the campus. And at that point is when we plan to have our heat recovery chiller plant installed. We're actually going to be replacing our 2 oldest chillers. We have 8 chillers on campus, and 2 of our oldest ones we're planning to replace with heat recovery chillers, so we can have that avoided capital cost that we would have had to spend anyways to replace the chillers. and instead put in heat recovery chillers that can make hot water along with a hot water thermal energy storage tank. So we can start supplying that north half of campus that's converted to hot water with water that we're making from our chilled water system, with heat recovered from that chilled water system. So at this point, we're still making the hot water for phase 1 and initially for phase 2 with heat exchangers that are making hot water from our steam system. And that was just so that we could get pipe in the ground, get the buildings converted, and get the load in place for the heat recovery chillers and the thermal energy storage tank, which is going to be the next step. And then we'll as soon as we can make the case for the funding, and essentially what we're doing is using our purchase utility savings for offsetting debt service for the additional work that we are going to do. So once you start capturing some savings, you can then use that to go out and get additional funding for projects. So doing it like this, I think it is very achievable. And we're happy to share numbers and get into more details with anyone who's interested in looking at that. In terms of implementation, this is what it looks like. A lot of trenches around campus with the pipe going in. We did use powder insulation, gilsulate that for the insulation on this first phase. Very easy to install, not so fun to work with if you have to dig it up ever. So where we did that, we went as deep as we could and tried to get below our other utilities. So we're not going to have to dig it up again because it's not fun to dig up. Just the powder nature of it clogs up our vacuum truck. You have to have a special vacuum to work in it and things like that. But much faster going in and lower cost in terms of insulation than having a pre-insulated pipe. But we're looking at for phase 2 what the best option is, and I probably take kind of different approaches for different areas of campus depending on the other utilities and how deep the pipe is. Let's see, we've got internal to the buildings. What's surprising is how much smaller your heat exchanger skid is if you have one for the hot water side. We had the good fortune of all of our buildings, for the most part, having hydronic hot water systems already inside the building. So we're just really tying into the mechanical rooms, not getting into the building systems themselves, and supplying the existing hot water systems with a new heat source. Instead of having steam to heat them, they now have this low temperature hot water. And in many cases now we're finding we don't even need a heat exchanger. We can just tie directly into the building system and supply the water directly from the loop to the building. We did use heat exchangers. This is showing a brazed plate heat exchanger, which is typical of what we put in the buildings. Mostly because we were concerned about old building systems and having closed loops that hadn't seen any outside water source for a long time getting opened up to the loop, and what it could do to the building systems and complications there. But we've did not have many problems on the buildings where we did tie in directly without a heat exchanger, and we're looking to do that more in the future to save costs and equipment maintenance things. On the right is actually a picture of a new building that was our first to tie directly into the hot water system without a retrofit. So this is showing a hot water skid here and a chill water skid down farther. But they take up a lot less room than our steam systems did in the building mechanical rooms. So big picture, this is our schematic of our buildings on the right side, showing the shell and tube heat exchangers, steam to hot water that we had for our buildings. And then the steam boiler plant in the middle here. And then we have 2 chiller plants in 2 different locations, 4 chillers in each of them with cooling towers. One of them has a thermal energy storage tank. And those are tied into our chill water distribution to the buildings. Of note is this previous system, those 2 heating and cooling systems were completely separate. But the new system, this is showing kind of final state of where we're headed with the heat recovery chillers providing the hot water. Now we're tying our chill water and our cooling and heating systems together, and not having to run the cooling towers as much. We're able to run the heat recovery chillers for the majority of the load, then adding chillers with cooling towers for the peak summer loads where we need it, and adding a hot water storage tank. And then our existing boiler plant essentially being there as a supplemental heat source as long as we want to keep those boilers around. But the ultimate goal being, like I said, a geo-exchange field where we can send our chill water into the ground and get a low temperature heat source for the chill water to keep running the heat recovery chiller plant in the winter. Potential of having air source heat pumps as well to supplement that. Those are two different systems we've looked at. And then serving the buildings either with or without heat exchangers. This is showing heat exchangers, but we're finding more and more we're not doing that. A couple lessons learned here to wrap up, and then we'll jump to questions. But this one's a pretty specific one, but kind of I wanted to give the general lesson learned I think is valuable. And we have many greenhouses, and one in particular had a lot of steam process where they would sterilize soil, and they have a trailer like this rigged up with a steam hose going into it to sterilize soil so they can kill microbes and things before they do their growing. And the consultant was going to replace it basically in kind with electric boiler to provide steam. Once we are eliminating the steam system, the hot water wouldn't do the sterilization. So they were going to put in 1,000 kilowatt electric boiler, but working with in more detail with this site, they have some autoclaves over here as well for sterilization. We were able to do some testing and build a new manifold for the soil sterilizer that was much more efficient and effective, and cut the total KW down to 191 with the testing, and then with a new manifold down to 121 KW. So, and then improve the whole process. So the overall reduction was just phenomenal. And I think that's where we found, if you just go with the original design, even in your building, heat exchangers, and instead of actually looking at loads and how you're meeting those loads, there's a lot of opportunity for downsizing, right sizing, but it's often downsizing your systems as you go through the process. And so there's some good savings there for sure. Last one I want to touch on is just, well, two of them really. One is when you're going through buildings, we have a lot of lab buildings with autoclaves and sterilizers. We have found that having self-contained autoclaves and sterilizers with their own generation instead of a standalone boiler to serve them is often a much more effective approach. That's kind of a specific one, but in case it applies, it gets away from having to deal with water quality and maintenance issues with the boiler system that you would be putting in. And then kitchens and dining commons are a tough one. We have a lot of steam equipment that you can replace with gas or electric, but oftentimes that's a big culture change, and it can also impact timing of the kitchen processes, workflow, things like that. So getting user buy-in really early on is important, and we're working through that process now in our phase 2 with our largest dining commons on campus getting converted. So I just wanted to throw those out there. We obviously have, this is kind of high level, and I have a lot more I could share if anyone's interested, but don't know the audience or what you guys are working on right now. So I'll open it up for any questions.
Thanks, Josh. This is always very fascinating. There's a lot going on at UC Davis. So we have a question from the audience that I think you already addressed, but I'm gonna say it anyway. They're wondering if you're laying new pipes in trenching, or you're reusing some of the old steam systems and kind of relining them.
Yeah, good question. We did look a lot at what are the ways you can do this, right? Because we had all the piping out there for the steam already, but the problem is, one of the reasons we needed to do this project, and one of the arguments we made for funding it, is a lot of that steam system was old and falling apart. Some of it was 60, 70, 80 years old, and needed to be replaced anyways. And so our argument was, instead of replacing that steam piping with new steam piping, let's put in something more efficient and effective, which is the hot water system. And so besides just the age and the condition of those pipes, they're also not the right sizes. The whole campus wasn't built at once, and so it was piecemealed together. And so it really, didn't always have the right sizes in terms of the design of the system. And then also having steam and condensate, different size pipes as well, doesn't really work with the hot water. So we did not find that effective in any of our distribution system. Not to mention that a lot of our pipes are in a concrete envelope about 10 feet underground with asbestos in it. So not really something we wanted to get into. So we left that all in the ground and went in with new hot water pipes, like I was showing, this HDPE piping that gets fusion welded. And that's complete. And that way we were able to design a completely new distribution system that was laid out for the entire campus, and we master planned that, the whole thing. So we got all the sizing right before we started doing the phases.
Thank you. I guess another question is the audience here, most of them are instructors of community colleges or technical schools. And do you think that there's different need of like workforce for a project like this, assuming that this could be adopted by other campuses around the country and so on?
Yeah, I mean, I will definitely put in a plug for trades in general. There's a huge need for workforce in the trades. I oversee the utilities operations on campus, and we have a lot of trouble finding good qualified tradespeople in electrical, controls, steam or pipe fitting, operations at the plant. All of those is just, it's very hard to find qualified people. I think that's going to be a huge need going forward. I think probably the biggest challenge actually that I've seen is the you guys have been talking a lot about control systems and how they for these, especially for larger buildings, commercial stuff, and on campuses. We have a really hard time hiring control engineers or control technicians that know anything about control systems. The only people often that will apply for our jobs are residential HVAC people who have never touched anything beyond a thermostat. And so getting somebody who knows anything about controls is often a huge challenge. And I think there's a huge opportunity there in terms of education and training going forward. I don't know if that answered your question.
Yeah, I think this is really sort of relevant for the audience. Thank you. And Josh, can you remind us, you have a UC Davis organizes an annual conference for facility managers of large campuses. Can you kind of maybe 30 seconds to plug in something there?
Yeah, and people can look it up. I don't have the link right with me, but if you look up Global Energy Manager Workshop at UC Davis, we have a number of, I think we just finished our 4th year, where we get everyone together to share best practices related to energy on campuses, energy projects like this, or like controls, or we have fault diagnostics. And so a lot of the folks on here have participated. And then we actually get together in the spring. So we've got one coming up this spring where we actually get people here in person and can show off some of our newer systems and do workshops together and learn from each other. So definitely would encourage people to attend. And one of the focuses on that is also the educational piece of it.
Awesome. Well, thanks again for joining us and showing all this wonderful work. And I'll see everybody else in the next session. Thanks, Josh.
Okay, thank you.